let's continue on energy of a simple harmonic oscillator. So simple harmonic oscillator means that the system that we discussed just now is about mass spring system as one kind of the simple harmonic oscillator. So within the discussion before this, we know that the object, the mass spring system, the block attached to the spring is in motion, oscillates. So it has kinetic energy which is equivalent to half mv squared. However, the V of the mass spring system is omega A sine omega t. So the whole bulk here is the V squared already. So initial, let's recall V is equivalent to omega A sine omega t plus phi. This is your V. And then for potential energy within the spring, okay, is equivalent to half kx squared. Let's recall back this from physics 1. And special case here for simple harmonic oscillator, the x is equivalent to a cos omega t plus phi. We know that at any instant, E total of the system, actually a combination of kinetic energy and potential energy within the spring. We don't have a potential energy in terms of gravity because the mass spring system that we discussed just now is horizontal mass spring system. So throughout the motion, there is no change in height. Therefore, the UG is equivalent to 0. Okay, and this is equivalent to, if you combine this one and this one into this equation, you will have this kind of, you may take out Ka squared outside. How come here we don't have Ka, isn't it? This is actually by make use of omega. Omega is equivalent to square root K over M, right? Omega squared equivalent to K over M. So if you want to substitute the omega, you may substitute K over M here, okay, with K over M here. Then you're going to cancel out the M, isn't it? Then you're going to left with Ka squared, which is also here you have, okay, Ka squared. Here also you have Ka squared. Then you're going to factorize and place the Ka squared outside. Then you have sin squared omega t plus phi plus cos squared omega t plus phi. Do not panic. This is actually a kind of theta, remember? This is also a kind of theta, right? So based on trigonometric identity, we're going to simplify this one. We're going to use sin squared theta plus cos squared theta is equivalent to 1. So the whole part here going to be equivalent to 1. Okay, become 1. That is why E total at any instant is equivalent to half Ka square. Right? Okay, in terms of graph, okay, when we observe the energy, kinetic and potential energy within a mass spring system to the respect of time, you are going to have this kind of pattern, sinusoidal wave function. The orange color here is the U. This one is US. And then the blue color here, this is K. Right? So at any instant, it is actually a combination between the K and the U. Let's say we take a look on this time. Right? T. Okay. At T. At any instant. So it's actually a combination between two readings. So E, Okay, at time t is equivalent to u at time t plus k at time t. So at any instant, it's actually a combination. If one of it become maximum, then the other one going to be 0. Okay, vice versa. Right. And at any instant, E total always equivalent to half Ka square. This is E total of the system. Right. And now, if we want to take a look on the K and U behavior or graph or graphical explanation, illustration versus position. Okay, we have two options, right? Whether from the point of view according to the time, or we want to take a look on according to the X, the position. So again, US here, right? US here, simply this column, and then US here, the formula is half kx square, right? And then the blue color here is kinetic energy half mv squared. Okay, and then if you want to have at this position, let's say, okay, at this x prime, okay, is equals, okay, half of it in term of kinetic, half of it in term of potential. Okay, at any instant, E total still equivalent to half Ka square. Right. So if let's say you want to take a look on this time, okay, x double prime, let's say. So it's actually combination between these two value. Okay, so Ex double prime equivalent to Us at x double prime plus K at x double prime. Right. And all the time E total equivalent to half Ka square. So now this is analysis on the energy of the simple harmonic oscillator, where we have a mass spring system. So at this instant, let's say the block is displaced, okay, from equilibrium position x equivalent to 0 and to the right, reaching positive A. Right, at this instant, okay, we are going to release the block. So the block going to attain maximum acceleration because it changed from static, from not moving to have some motion. So the A of it going to be maximum. At positive A, okay, what will happen in terms of potential energy, okay, will be maximum 100%. This is also equivalent to the E total, right? And then after that, when the block move and reach the first time of the x equivalent to 0, as we know, Fs here going to be 0 because Fs is equivalent to negative Kx. Here x is 0. At this instant, you do have Fs. Okay, it is maximum as well. Okay, at this instant, Fs equivalent to negative Kx, which is 0, because the x is 0. When Fs is 0, okay, potential energy, okay, is also equivalent to 0 if you refer to this one. Potential energy will be 0, right? Okay, if you refer to this, okay, potential energy will be 0. And then your kinetic energy at this instant will be maximum because kinetic energy is equivalent to half mv square. Kinetic energy equivalent to half mv square. Since here will be V maximum, so kinetic also going to be maximum, which is equivalent to E total. which is 100%. Right. And then due to the conservation of momentum and law of inertia, even though the Fs is 0, the block still going to proceed to the left until it reach negative A position and stop a moment. And then after that, okay, when it stop a moment, the V going to be 0. So if you see here, V going to be 0, kinetic energy going to be 0. All of the energy in terms of potential energy, 100%, which is equivalent to E total, which is half Ka squared. Right? And then the block going to be moved to the right by the Fs. Here you do have Fs. You do have Fs here, equivalent to negative K times negative A. That is why your Fs is to the right. It's become positive right now. Okay. And then again from negative A is going to move to the equilibrium position. Reaching equilibrium position, again the Fs going to be 0. The potential energy going to be 0. Alright. And the V going to be maximum. And kinetic energy going to be maximum, which is equivalent to the E total, which is half Ka squared. Your V, bear in mind, for this position and this position is V max equivalent to omega A. Okay, negative here direction. This is to the left. This is to the right. Okay. And then here is the period. This is, we are going at the starting. This is 1/4, quarter of the motion, time taken. This is half of the motion. That is why half period. Because period is the time taken to do or make a complete motion or oscillation. And again, when it reach position of A, positive A, okay, kinetic energy is stop a moment. Kinetic energy will be 0. Velocity will be 0. Position at A, and then it's going to have potential energy maximum, which is equivalent to E total. And then it's going to have Fs, which is to the left, which is similar to this situation in situation A. Right. So this is until E, okay, you have one complete oscillation, okay, or vibration, which is the time taken is period. Right. Let's say at the instant it is leaving the A, positive A, but then not yet reaching the equilibrium, which is X equivalent to 0. Okay, at this instant, this is actually, at this instant, it must be a combination. E total of the system must be equivalent to kinetic energy plus potential energy. But all the time, okay, the E total is conserved or maintain the same thing, because we consider there is no friction or internal friction or air drag at all. That is why we can put it as simple harmonic oscillator. Energy of simple harmonic oscillator, this is as I mentioned just now. Okay, E at any instant is actually combination of K and U. Right, the K in terms of position, according to the position, is half mv squared, and the U is equivalent to half Ka squared. All the time must be equivalent to E total, which is half Ka squared. Alright, so from here you may rearrange the equation, put up the V as your interest, then you will have this one. Okay, you may take out square root K over M outside, okay, which you are going to give this value. You must be able to derive this part. So for this equation, it is very important, okay, that you all must be able to derive this equation from here. Right, what is the final unit of your V? It must be meter per second. The SI unit must be meter per second. harmonic oscillators as models. So actually, how scientists be able to learn the behavior of the substance, okay, especially solid. Okay, if you refer to this graph, the potential energy within the solid structure or matter, okay, almost the same shape to the potential energy, right? The orange color here almost assemble the dashed line here. That is how scientists be able to assume that the energy between that bond between one atom to another atom, the neighboring atoms, similar to the behavior of the simple spring like this, right? So example 15.3. Okay, so this is actually the diagram that we discussed just now. Okay, it's 0.5 kilogram card connected to a light spring for which the force constant is 20 Newton per meter, oscillates on a frictionless horizontal air trap. Use an energy approach to respond to the question below. So it is requested for us to use energy approach. Alright. Calculate the maximum speed of the card if the amplitude of the motion is 3 cm. We need to calculate maximum speed. E equivalent to half Ka square equivalent to half mv max square. What is the potential energy? Potential energy is equivalent to half K x square. When this one is max, the position is actually 0, right? That is why the formula on the left with half mv max square. Alright, so V max is equivalent to square root K over M times A. Because, if you directly memorize this one, right? Let's say you memorize this one. V max equivalent to square root K over M A square minus X square. Let's say you don't want to derive from here. You don't want to derive it from here. You always memorize this one. What should you do? It's okay as well. But you need to know V only maximum whenever the X is 0. Okay. Then back to square one, right? You will get this equation again. Okay. So if you substitute the rest of the value, you will get this answer. And then part B, what is the velocity of the card when the position is 2 cm? So this is not the amplitude, not the equilibrium. Okay, at 2 cm, use this formula directly, right? Substitute the A is 0.03, must be in SI unit because this one is all of this in SI unit. So max squared minus 0.02 meter squared. Then you will get this answer. At any time that it reached this position, this is the magnitude of it, positive and negative, depending whether the object is moving to the left or to the right. C. Compute the kinetic energy and potential energy of the system when the position of the card is 2 cm still. But then now we are interested in kinetic and potential energies. So kinetic is half mv squared. V here must be V that you already calculate in B, which is value of V at 2 cm. This one. Okay, regardless of positive negative, because when talking about kinetic energy, it's kind of energy. There is no direction. It's scalar only. So take the magnitude only. And for potential energy, directly half Kx square. You already have your K. And then place your, substitute your X. This is your answer. So if you combine this, you will get the E total, which is equivalent to half Ka square actually. Right, the cut in this example could have been set into motion by releasing the card from rest at X equivalent to 3 cm. What if the card were released from the same position but with an initial velocity which is negative 0.1 meter per second? What are the new amplitude and maximum speed of the card? So we need to use the E total equivalent to K plus US again, but then you do have your V at this instant, which is equivalent to this given. Alright, then from here you will get your E total and proceed with E total equivalent to half Ka squared. From here you will get your A, which is not 0.03 anymore. It must be add up something, right? Bigger. And then after that, you may also calculate your Vmax according to the E total equivalent to Vmax. Because at maximum velocity means that kinetic energy maximum, the potential energy is already 0. This is actually coming from E equivalent to K plus US. If this one is maximum, this is total, okay? This one already 0. That is why you have this formula. Right? And then solve for Vmax. This is your answer. Okay, now let's proceed to the drive mechanism for non-electric sewing machine. This is actually in terms of how come vibration can be related to the circular motion. Okay, in subtopic 15.4. Okay, so if you recall your grandmother, okay, this is the traditional sewing machine. Okay, we place the foot on this pedal, isn't it? And then we're going to move our foot up and down, and then it's going to be transferred to this what we call it, drive wheel. So the drive wheel here going to rotate. So that is how vibration can be converted into rotational or circular motion. Similar to this situation, let's say this is a turntable, right? I believe we still remember this. Okay, we do have this in our physics 1. Okay, let's say we have a turntable. Okay, an object is placed at this position. Okay, having radius r from this disc. Okay, and then now it's going to rotate. Okay, according to this direction, which is counterclockwise. Okay, we are going to have our lamp on the top, so that the shadow of the object here going to be on the screen at the bottom of the system. So the moment of this object is moving, so the shadow also going to be moving. This one is moving, rotating. Okay, counterclockwise direction. However, this one is moved to the left and to the right, isn't it? That is how we can relate circular motion to the vibration. Okay, this is to be particular on how, okay, we are going to compare simple harmonic motion with uniform circular motion. So, at the instant, take a look on figure A. We have an object having a place at P position. Okay, at this instant, there is no motion yet. Okay, at T equivalent to 0, it already has phi. Okay, angular displacement, the initial angular displacement. And then, or simply known as phase angle. Now, it's going to move, okay, from this position to this position with certain angular frequency of omega. Okay, the image of this point P is at point Q. Okay, where in terms of linear displacement, it has X and Y position from the origin. Okay, at any instant from the center of the circle, this point P is having A as the radius. So now, from the reference axis or positive x-axis, when it reaches this P position, this new position, this point P now is making angle of angular displacement, right? So the theta is equivalent to omega t plus phi, the initial, because initially it has the phi. And then, okay, this is in terms of the theta. Okay, how to have the x here? To have the x, okay, we're going to use a cos theta, isn't it? A cos theta. So x equivalent to a cos theta. So our theta is equivalent to omega t plus phi. Right. And then the x here keep on changing or varied according to the time, if you are using cosine function here. Then in terms of velocity, at this point, okay, at this position, object here has tangential velocity, the red color one here. Okay, it has component. Okay, our interest right now is x, so it does have vx. Okay, so while this point is rotating counterclockwise, the image of it at point Q seems like going to move to the left, right? And then after it reach this point, it's going to move. After it reach this point, it's going to move to the right, and so on and so on. At any instant, when you do have changes in terms of v, okay, you're going to have your centripetal acceleration towards the center of the circle, isn't it? And at this instant, you do have your ax as well, because you are in motion from static to certain amount of omega or displacement, right? So the velocity of the x component of the velocity will be omega a sine omega t plus phi. This is actually can be written as your vx, right? Which is vx, okay, is actually dx over dt, right? Which is, what are we doing? We are going to differentiate the x to the respect of time. What is our x? What is our x? Here is our x. That is how we are going to have this one. How come? Differentiating, we want to differentiate what? The things, the item with the time, which is this one. Okay, so but then it's a part of function of cosine, so you have to differentiate cosine first. Differentiate cosine will give you negative sin. Okay, negative sin, this is a constant remain, and then now you're going to differentiate the one that with the t, which is omega. So omega t differentiated to the respect of t, you will have with omega. That omega going to be placed in front as a constant. That is how you have this as your final product for the v along x. Example 15.4. Circular motion with constant angular speed. The ball in the figure rotates counterclockwise in a circle of radius 3 meter with a constant angular speed of 8 radian per second. At t equivalent to 0, its shadow has an x coordinate of 2 meter and it's moving to the right. Okay, determine the x coordinate of the shadow as a function of time in SI unit. Alright, so let's recall back that x equivalent to a cos omega t plus phi, and then solve for your phi firstly, right? And then you will get here positive, negative, possibility of 48.2 degree, or in terms of radian, this is the one. And then you are going to take your x again, substitute the information already given for your a, and then calculate your omega, and then your phi. Why is it negative? Because it is moving to the, okay, according to the question just now, it's motion to the right. Okay, because it's moving to the right. Right. So if you visualize, okay, reference axis here, x, y, okay, so it is moving to the right. So the shadow is somewhere here, right, like that. So the theta must be somewhere here. Here is your angle. That is why your angle is negative, your phi, right? Now example 15.4 again, part B. Find the x component of the shadow's velocity and acceleration at any time t. So means that we want to have the expression because at any time of t. So v is dx over dt. Again, substitute. This is actually coming from, for your v, x is equivalent to negative a omega sine omega t plus phi. This is the general equation. Then you substitute everything that we already calculated into this equation. That is how you manage to get this one. And for A, your original equation is actually ax equivalent to negative omega squared a cos omega t plus phi. Alright, then you will have this as your final answer.